Before we go into the next type of subatomic particle, I just want you to have a think about this meson. Now remember, a meson is, from what a meson is from the previous video. Now this is a meson. This is called a kaon, okay? So kaons are a meson. So a kaon is represented by K+. So now one thing I would tell you about this kaon is it has a strangeness of +1. So let's have a think very carefully about what we can tell about this particle, this meson. So first of all, we know it's a meson, so that means it's made up of a quark and an antiquark. Okay? So thinking about, maybe looking back at your notes from the previous video, what quark and antiquark must be put together in order to make this work? Well, first of all, it's got a strangeness of +1. Now that should be a teller straight away. There's only one particle that we're allowed to use that has a strangeness of +1, and that is an anti-strange. Look back at the table from previous. We have an anti-strange has a strangeness of +1. Well, there's only one quark and one antiquark, so we know that the antiquark now must be an anti-strange quark. So we've narrowed down the fact that this must be an anti-strange quark because it's got a strangeness of +1 overall. What else do we notice about this kaon? Well, it's +1 overall. It's a positively charged kaon. So, if it's got a charge of +1, try and remember what was the charge on an anti-strange quark. Be careful. Remember, a strange quark followed the down quark, which are very similar, apart from the strangeness. So a normal strange quark has a charge of minus a third. So an anti-strange quark has a charge of plus a third. Again, if you're not sure of why that is, go back, have a look at the previous video, that will remind you. So we've got a charge of plus a third, but we need to make +1 overall. So what must my quark be in order to make the quark-antiquark pair for this meson? We know it's got a strangeness of 1. We've dealt with the strangeness. We're now dealing with the charge. The fact that it's a meson tells us that it's a quark-antiquark pair. We're missing positive 2/3 of charge. Well, which quark has that? Yep, it's an up quark. Because an up quark has a charge of plus 2/3. When we add those together, we get a total charge equals 1. We also have fixed the strangeness, because that also has a strangeness of +1. So we can say that a kaon exists as a up anti-strange meson. And that's a really useful kind of thought process to go through there, because you could be asked questions like that where you're given a particle and you've got all these building blocks that could make it up. You know that it's a meson, so it's got to be a quark-antiquark. You know that it's got strangeness, so it's got to have a strangeness quark in it. It's got to have a charge. How can we make up that charge? So we use all of our building blocks. It's always useful to have a table of particles next to you, and you are given the particle charges in your exam. So that's a really, really important kind of thought process to go through with mesons. Okay, and not just mesons, other particles as well, even baryons, because you know baryons have 3 quarks in them. And you can also have antibaryons, etc., etc. So you just got to be wary of that. You don't get anti-mesons. They're always quark-antiquark. You don't get anything else apart from quark-antiquark pairs in the meson set. Okay? So that's how you might work out a meson. That's kind of some assumptions. And that's a nice thought process to have guided you through there. What I want to talk about now is another type of classification of particles that we've not gotten to yet. It's leptons. Now, leptons, again, another type of particle. You know leptons really well. You've probably come across leptons in every other science class, because one of the favorite leptons to utilize is the electron. It's likely you will have come across as well some other leptons, for example, like an electron neutrino. Now there are other leptons to consider. You've got muons. You've also got muon neutrinos. You've also got tors. And you've also got tor neutrinos. One thing I will say about these is the ones you really need to be aware of are the electron and electron neutrinos. One thing I will do is I will put the symbols in here. So a muon has a mu symbol because it's mu. So it looks a bit more like that. And a muon neutrino is that. And a tor is like a funny looking T. It's kind of like a curly T at the top there. And guess what a tor neutrino looks like? Yep, you got it. You got the curly T at the top there. So that's kind of what all those different particles are represented by. But unfortunately, it doesn't stop there, because we do have opposites and properties of these particles that you need to know about. So let's have a look at some properties. Now, as we well know, these all have charge. So let's talk about charge. What's the charge on an electron? Well, hopefully you remember, -1e, because they're all proportions of E, same as with the protons and the neutrons and the quarks. We all do things in terms of the charge on an electron. So in this case, we'll just call it charge in terms of E. So this is a neutrino. The key in the word is neut. Guess what the charge is? 0. Muon, -1. Muon neutrino, neut. Hints in the name, tor, -1. Neut, 0. So obviously you need to be aware of these charges in terms of that. Now, nicely, the particle that you see there indicates the charge. If you see a minus above it, it means it's negatively charged by 1. If it's got a plus in front of it, it's positively charged by 1. So it does make sense for the most part, and these neutrinos have no charge values associated with them, so they are neutral. And yes, there is another quantity that we need to consider. Think about lepton number. Now, lepton number is another quantity that needs to be conserved in kind of reactions that we look at. Now, very simply, the lepton number of all leptons is really nicely just 1 in every case, because they are all leptons. However, there is an opposite way round. And I'm just going to use one example. I'm not going to complete the full table this time, because I don't think it's necessary after I did the one for the quarks. But each one of these has an antiparticle. So we are going to focus on my next page, antielectron and an antielectron neutrino. So, an antielectron, well, does anyone know what an antielectron is called? Well, it's otherwise known as a positron. So a positron is the opposite, the antiparticle of an electron. Symbol E+. It's a positron. It's not an electron, it's a positron. Guess what its charge is? +1. Guess what its lepton number is? Everything is an opposite in an antiparticle. The lepton numbers were 1 or before. Guess what? -1. What about an electron neutrino? An antielectron neutrino. Well, it's still, let's put the symbol in here. So, follows the same convention as before. We just put the bar over the top, so VE bar. So, it's neutral, charge is 0. Lepton number, yep, you got it, -1. And the rest of the particles follow suit with that. So let's just take you back to this other page again. The rest of the particles follow suit. You get antimuons, +1, -1. Antimuon neutrinos, 0. Obviously the bar at the top, -1. Anti-Tor, +1, -1. Anti-Tor neutrino, bar over the top, -1. So hopefully you're seeing how we can look at antiparticles and utilize them to explain different properties. Now, these ones are the most important because you are going to utilize these in decay equations, because one of the things that we might have talked about before in previous videos is that actually the decay process that's going on, we haven't told you the whole story. And in the next video, we are going to tell you the whole story, and we're going to explain why that works and how that works.